We talked about linear functions the entire fall. We've started learning about quadratic this week. So now we're going to talk about how to tell the difference between linear and quadratic. First of all, we can look at the equation and tell from the equation. So linear would have an x with no exponent. It would have an x or a y or both. So remember, we saw linear equations like this. That was standard form. We saw them like this. That was slope-intercept form. We saw just a y. That was a horizontal line. We saw just an x. That was a vertical line, but no exponents anywhere. So quadratic has an x squared. The highest power is going to be 2. Now in Algebra 1, we're only going to see quadratics with an x squared. In Algebra 2, you'll see them with a y squared. So here's the parent function, y equals x squared. Here's the, you might see something like this. You might see something like this. But the squared is always going to be associated with the x. Now, I said this was the parent function. I should have pointed out that the linear parent function is y equals x. So, from a graph, linear is going to be a straight line, quadratic is going to be a U. We call that a parabola. It also could be upside down. So from a table of values, you can tell whether an equation is linear or quadratic. It's actually quite easy to tell. You look at the differences. So linear, if it's a function, you're not going to see the same y value twice. The first difference is the same for all the y values. So here, we're going, first check your x column and make sure you're going up by the same thing. So I'm going up 1, 2, 3, 4. So now let's check the y values. This is plus 2, plus 2, plus 2, plus 2. That's how I know it's linear. It's the same first difference is what I'm going to call that. Remember, that's also the slope. If it's linear, it has a constant slope. But on quadratic, usually you'll see at some point, remember how we arrowed through the table on the calculator to see when the symmetry quit? So you'll see symmetry. You'll see the same y value repeat. We just don't have that part right here. But the second difference is going to be the same. First, let's check x. It's going up by 1, 2, 3, 4. Okay, so it's going up one number. So let's check the y. Here we add 1, we add 3, we add 5, and we add 7. Now let's check this. Those aren't the same at all, so it's not linear. Check this, the second difference. Check the difference of the difference. From 1 to 3 adds 2. 3 to 5 adds 2. 5 to 7 adds 2. If the second difference is the same, second difference, we know it's quadratic. First difference, linear. Second difference, quadratic. So let's look at some examples. Let's check these. First of all, x is going up by 1 each time. Y is going down by 4, down by 4, down by 4, down by 4, down 4, down 4, linear. First difference the same is linear. This one, x is going up by 1 each time. Add 5, add 3, add 1, subtract 1, subtract 3, subtract 5. That's not at all the same. Let's check the second difference. Subtract 2, subtract 2, subtract 2, subtract 2, subtract 2. That's quadratic. The first difference wasn't the same at all, but the second difference was. We'll check another one. Does x go up by 1 each time? Yes. Here we go. Add 3, add 3, add 3, add 3, add 3, add 3. Well, that's linear because all the first differences are the same. This one, does x go up by 1 each time? Yes. Okay, this one would be add 18, add 6, add 3, add 3, add 6, add 18. Looks like there's a pattern here, but Let's check this. Minus 12 minus 3 minus nothing plus 3 plus 12. Not at all the same. This one's neither. It is neither linear nor quadratic. I do want to show you something though. Do you see how this divides by 3 every time? And then it turns around and it starts multiplying by 3. Interesting pattern, but it is neither linear nor quadratic.